All right, so yeah, this talk is about Julia and Python. And I have to admit that the talk title that I submitted 5 months ago or whatever was a little aspirational, at least the better together part. So we'll see if we get to a little bit of how the two languages can interact. But at the very least, it's about Julia and Python astronomy. All right, so Julia is a new language focused specifically on technical computing. It's a general purpose, it's designed to be a general purpose language, but at least initially their focus is on this niche that we're all in. Right? So just to get a rough idea, how many people have heard of Julia? Okay, so almost everybody. Yeah, so why am I giving this talk about Julia at this conference about Python? And by the way, thank you for the organizers for letting me get this in here. So one reason is, it is a language aimed at exactly what we're doing. So it's kind of interesting to look at the design decisions they're making and see how they relate to what's available in Python. Another is, what was the other reason? Oh yeah, so it's also, there's a lot of similarities between Julia and a lot of stuff that's going on in Python itself. Stuff like Numba, for example, is making a lot of similar design decisions to Julia, so there's some overlap there. And also, learning about Julia and kind of having my ear to the ground and what's going on here has actually helped me become a better Python programmer. So you might find the same if you get interested in it. So I do want to say that I love Python. I still do actually all my research work in Python. I kind of just do look at Julia as a side thing for fun. Obviously, we all love the great ecosystem that Python has. It's a beautiful language. I still love significant white space, all that, right? I'm not going to tell you to stop using Python. But, right, we all run into these things, right? Some things and problems are just, they're difficult to vectorize, or just they're very awkward, or they could be impossible. And in Python, we're kind of in this system where we have to write vectorized code for anything that happens, anything that's like performance sensitive, right? It's possible to drop down to C using Python or any of these other tools for the performance sensitive parts, but it's not easy. Some cases, like Nathan was showing in the first talk, some cases are easy, but in general, that's not going to be the case. And at some level, I feel like you have to know both C and Python to really make that work, which is kind of a huge reach for a lot of people who are just starting out. And then one other angle is, as library writers, having to write array-oriented APIs can be kind of constraining. And to tell you what I mean by that, I'm going to give you a short Python example here. Suppose you want to design something to deal with points in 2 dimensions. Very simple, right? You might want the ability to talk about a point, which has an x and y coordinates. But what we end up doing in Python a lot of times is we want to make it vectorized. So we make a class, instead of a class called point with x and y, we have a class called points that has 2 x and y vectors. And you can then only talk about a set of points together, whereas you might like the ability to talk about a single point, right? So this is like, for example, what happens in the coordinates package in Astronomy. That's how it works. It's a set of points together, which totally makes sense as a design decision in Python. So in general, all these things are what people call the two-language problem, where you have this high-level dynamic language that we all love for rapid development, and for the performance-sensitive parts, you drop down to a compile language like C, and then you have some interface code to go between. So this is the problem that Julia is trying to address by trying to be a high-level dynamic language that you can also write fast code in the same language. So if you go to Julia's homepage, they have this infamous set of benchmarks. They're quite contentious at times. And the reason they're contentious is because, this set of micro benchmarks are just a few lines of code each. And the thing is, they're not like the idiomatic way you would write something fast in Python, right? They're really just designed to show if you wrote some algorithm in the language itself without trying to optimize it, how fast would it be, right? So they're testing things like Fibonacci is testing how fast you can do recursion. This one tests complex arithmetic, that sort of thing, right? So Python does pretty well for an interpreted language, but Julia, you can see, so these times are relative to C. So for this, Julia is the same speed as C. Python is 20 times slower, that sort of thing, right? So you can see it's doing pretty well within factor 1 or 2 of C. So it's fast, but it still feels dynamic. So this is the implementation of that benchmark that does complex arithmetic. You can see it looks kind of more or less like Python. You just change def to function. The iteration is a little different. You have to put some end statements in there, so just leaving blank space, which you may or may not like. But it's very readable, pretty clean. Yeah, one-based indexing is something that a lot of people can't get over, I've found.
They did that because of MATLAB, right?
Yeah, so the history, I think, is that the developers came from MATLAB background. So this is, I don't know MATLAB at all, but this is apparently pretty similar to MATLAB syntax. And even at a very low level, it still feels dynamic. So if you look a little deeper, this is actually how complex numbers are defined and how complex arithmetic is defined in Julia itself. So yeah, this is declaring that a complex number is made up of 2 individual numbers. This is a short function syntax that Julia has to say, like, the real function on this number equals this. And then so this is defining plus on a complex number. So when I saw this, it's pretty awesome that you can write code like this and it compiles to run as fast as C code. So I don't have time to go too in-depth on Julia, obviously, but a few more enticements. There's a few things that kind of struck me about it. You can call C and Fortran directly with 0 overhead, no wrappers. So this is how you would call the sign function from the math library in C. You give it the name of the function you want to call, where it is. You have to tell it the output and input types, and then you just pass it the number you want to feed to the function. So you can start up Julia, and the first thing you write in Julia can be a wrapper for a C function, which is pretty impressive, hard to say in Python. Something that might get people in working in AstroPy is that you can have 0 overhead quantities. By overhead here, I mean runtime overhead. There is a compile step. But I can talk about that a little more later if people are interested. So what happens here is, so I'm adding 1 volt plus 2 volts. And what will happen is that at compile time, the first time the function's run, it will check that the units match, and it won't allow the operation if they don't. Because of how the language works, it's a lot easier to do automatic differentiation. So this is not numeric differentiation, but actually calculating exact derivatives, which is really useful in optimization problems. You can do it in Python, but it's not quite as easy. And you can even drop down and inspect the native code that the compiler is going to generate. So on the right there, I have an example of asking what is the native code for multiplying 2 complex numbers. And so this is like what you would get if you compiled C and looked at what the machine code is actually being generated as. I don't really read assembly, but this is this is apparently very efficient. If you can fit it on a slide, it's efficient. And then one other thing is that multi-threading is on its way. It's in the language right now, but it's off by default because they're still kind of working on that feature. But it is for sure going to happen. All right, so to get back to the Python angle. So Julia and Python have a pretty good history of working together already, I think. The Jupyter guys, which is now called that because of Julia, Py, and Python and R, if you didn't know where the name came from. So they got together a few years ago and made sure the notebooks could work with Julia. So this is a screenshot from, if you go to juliabox.org, you can get a interactive, you can just try Julia in the web browser and you get a notebook. There's a PyCall package in Julia to call any package in Python that exists. So this is an example of using NumPy from within Julia, which for this you wouldn't really need to do because there's Julia equivalents to this, but there's a lot of cases where Julia, Python has this huge ecosystem. Something you need might not exist in Julia. So you just do this Py import NumPy as NP, and then this is from within Julia, but you can just call NumPy with a syntax like you would see in Python. And even stuff like, so you can even use SciPy like this. And so this example on the right is just saying, I can even define a function in Julia, f of x, and call a optimizer from SciPy that will call that function. All right, so to get to the astronomy specific part, so people might ask, so is there any like AstroPy equivalent in Julia? The very short answer is no, there isn't. If there were, it would be this Julia Astro organization. And how the organization is set up a little differently. It's not a single package. In Julia, the style is more to have separate packages for different functionality as much as possible. And to use GitHub organizations to sort of direct people to the thing they want to use and to make sure that the ecosystem is being developed in the same way. So what's there right now is there's a couple of very small pure Julia packages, Cosmology and Dust Extinction, that were honestly, I think, kind of written. I didn't write Cosmology, I wrote Dust Extinction. For me, it was more just as playing around. This is the oldest one, and it's very short. It's like 200 lines, but it does a lot of the same sort of stuff that AstroPy Cosmology does. The other three here are actually wrappers for C libraries that are also used in AstroPy. I said earlier that you could wrap C code with, or you could call C code with no wrappers, which is kind of true, but you don't want to write these C call statements all over the place. So what people end up doing is writing like nice Julia interfaces that do those C calls for you, right? So you still have wrappers, but they're extremely easy to write, and it's all in Julia. I want to point out this one in particular because I didn't really have my ear that close to the ground on this, but my understanding is from overhearing what's going on, there's a lot of work put into making sure that IRFA, which used to be is derived from SOFA, was released under a open source license by the AstroPy guys. So that has already benefited other languages. All right, so besides the organization, there's a few other packages for astronomy that I just want to mention that are available in the package manager. There's one for ephemerides. SkyCoords does radio astronomy, apparently. OIFITS is a extension to the FITS format for optical and infrared formats. And then I have another package for playing around with a Julia implementation of SkyCoords, like the AstroPy ones. And then there's actually a YT wrapper, which I think just calls Python using PyCall. And I've seen a few other packages out there in the wild that are not registered. So it's quite small at this point, I would say. Yeah, so actually, total, I didn't say. I took a look, and there's about 5,000 lines of Julia total in all these packages. So that's smaller than many of the AstroPy sub-packages. So just to give you an example of this SkyCoords package, which was sort of, for me, just sort of playing around what would it look like if you implemented this, implemented AstroPy's coordinate system in Julia, and really just a few of the very simplest transformations. So like I said earlier, the nice thing here is that you don't necessarily need to do everything vectorized. You can talk about single sets of coordinates. So this example is just saying, create a point in coordinate space in the ICRS system, and then convert it to galactic coordinates. So it works, great. But the interesting thing here is that you can then make sets of coordinates. So this is saying, create this point 3 times using array comprehension syntax like you would in Python. And this is stored very efficiently. So if you then ask what the size of this vector is, it's 48 bytes. So that's 16 bytes per thing, per coordinate object. So it's being stored very efficiently in line, sort of like you would get in C with a C struct. And so if you compare, converting coordinates is not like probably going to be your bottleneck, but it's kind of interesting to look at how fast you can do this. So in the Python coordinate library, so this is the time it takes to do a conversion between 2 systems with scaling with number of coordinates in log space. This is from 1 coordinate to 1,000,000 over here. So in Python, you get scaling like you'd expect once you're past 100,000 coordinates, but there's this overhead that's associated with, well, the coordinate guys would know better. I'm not exactly sure where that comes from, but yeah, you would expect some overhead in Python associated with just doing function calls, that sort of thing. But in Julia, it scales all the way down to, so these are all the Julia lines, scales all the way down to 1 coordinate. You get the same performance. So, another thing people will say is, all right, so what's the future plan here? Are we like eventually in 5 or 10 years going to have to rewrite all our Python? So my response to this is kind of that, all right, so some of it, you're going to maybe rewrap some C libraries. But really, I think typing is not the hard part. Rewriting code is not actually all that bad. The hard part is figuring out what the code is supposed to do. So take this coordinate example again. A lot of hard work was put in by the AstroPy developers on figuring out exactly what the coordinate systems are supposed to be. And you can even go to this AstroPy /coordinates benchmarks on GitHub. And there's this huge page listing all these coordinate conversions and comparing all these different tools and making sure that AstroPy is using the right numbers that underlie the coordinate conversions, right? So if you already have that, it was actually very simple to just look at that and say like, oh, I'm just going to like translate this to Julia, right? I think that part is not actually the difficult part. So I'm going to leave you with a couple takeaways from Julia that maybe are applicable to Python. So one is I really liked Christoph's diagram of how you develop code yesterday. So he had this thing like this. This is kind of the model that I agree with that he was, I think, proposing is that most of the time you write Python. Eventually, some parts you might want to optimize using C and Python, right? When you get to them. If you find that the C is getting to be a lot, I think it seems like it might be a good idea to abstract that part into a library that you can then call from other languages. So if this part is getting fatter than it seemed like initially should have been, then maybe it's time to say like, oh, this is actually a lot of code that's in the C layer. Maybe we should abstract that out and make it a library that both Python and other things can use, instead of just writing a ton of like Python code that can only be used from Python. Oops. So the benefit of this is that not only can you call that from Julia, you can also call it from, in the future, something like PyPy, which if you write Python code is not possible. All right, and then I think I'm running out of time. I want to leave some time for questions, so I'm going to skip the last little point, which is about modules. Yeah, you can ask me about that if you want. All right. Thanks.
Maybe one question.
So I'm really curious about the other direction. Right? So you said you were calling Python from Julia. I'm guessing from your original title you wanted to be able to do it the other way. Is there a future in that? Right? I know you don't want to have two languages, but honestly, I think that sounds like an amazing thing to do.
Yeah, so there is a package in Python called PyJulia that, so in the same way that you can embed a Python interpreter, there's a C API to do that in another language. You can do that with Julia also. You can embed the Julia runtime in Python. So that's what PyJulia does. So you can write Julia code and then call it from Python. Honestly, it's not very developed because I think not many people are interested in doing that. And B, I think it would probably be better if you're going to go that route to do something like Numba, which is doing something similar to what Julia does anyway, and is more geared towards Python. You're writing basically Python code. So I'm not sure that there's a direct benefit like that. I do think that I think Julia is influencing some, it's definitely having an influence on the design of stuff like Numba. So that might be the best way it can really help Python. But yeah, in the talk title, I was like hoping I could find some other angles, but yeah, I'm not sure what they are yet.
Thanks, speaker again.